Okay. So far we were discussing renormalization group of spin system, right, 5-4 theory, renormalization 5-4 theory, and I have computed, I basically showed you how the two parameters R naught and U naught, they were changing with under coarse graining and rescaling, right. I did that before before in the last class. Okay. Now, this is a parameter R naught and U naught are changing under this RGO operations. Now, we are going to look at fixed point, that means what are the values when, well, I will show you what is meant by fixed point. Okay. So, this is what is called RG fixed point, and this was first discovered or initiated by Wilson and Fisher, okay. And this is taken from this material by Kopitz. So, just to recap, we were working with 5-4 theory, where the free energy is this. Okay. So, their parameters, phi is the spin field, where R naught is a parameter, C naught is a parameter and U naught is a parameter, and I showed you how R naught and U naught changed under two operations. One was coarse graining. So, we averaged over spins, right, and then when you averaged over spins, then these blocks became big blocks, then we to rescale it so that it looks like original spin system. Okay. But of course, in this process R naught became R prime and C naught was unchanged. Please keep in mind the C naught was unchanged, but U naught also got changed. And what were the formulas? The formulas for R was, R prime is after the operation, coarse graining and rescaling, earlier was R naught. Okay. So, the correction is sitting here under coarse graining, and this B squared came because of rescaling. Okay. And ZB you can ignore it for this course, ZB is 1. And U prime, the coupling constant for 5-4 theory, it started from U naught, but then became U prime, and this is because of rescaling, but this is a correction due to coarse graining. Okay. So, please remember the B was the parameter, no. So, the block size was enhanced by factor B. So, my earlier spins were like that, but then I took B blocks, size of B block. So, let us say our initial size was delta, then under coarse graining it became B times delta. So, this was B times delta. Okay. So, B was the scaling parameter, coarse graining parameter. Okay. So, it turns out that in field theory, instead of using B, we use this formula e to the power L. Okay. B is greater than 1, right. The example we did was B was 4, the box size was, blocking was like 16, 4 by 4 in 2D. But here if you use B is equal to e to the power L, L will be greater than 0. L equal to 0 corresponds to B equal to 1, which is identity operation, no coarse graining. Okay. So, L is greater than 0. Okay. So, in fact, you see that this equations become bit better with L. So, instead of B we use L variable, and ZB is 1. Okay. So, I am going to write a differential equation. Okay. So, basically I am going to say R prime minus R 0. So, it went from R naught to R prime. Okay. So, that is my, I am going to write, this is my change in variation divided by B, or B is e to the power L. Okay. So, that is a subtraction I am doing. Okay. So, R L. So, please remember that instead of B I am using L. So, this is algebra which I am skipping right now. So, this implies R prime minus R 0 divided by D L. Okay. And I am using L to be small. Okay. So, then this becomes D R L by D L. Is that clear? Okay. So, this is a differential equation now, and the right hand side will be 2 minus eta L and like that. Eta is Okay, so right now, okay, so this is what we get. ZL is 1 and B is e to power L. V squared will be e to power 2L. Eta L is 1, eta L is 0 right now. Eta L, this is 0 and ZL is 1. Ignore eta L for time being. Okay, I mean, these are slightly more complicated stuff which we will not do in this course. And same thing for UL, we get this equation. Skipping algebra, this is what we get. Okay, eta L is 0 and ZL is 1. Now I make another change of variable. These equations look reasonably complicated. We make another change of variable. RL is converted to RL bar, okay, which includes C naught and lambda naught 0, lambda 0. Lambda 0, what was lambda 0? It was the highest wave number, and then we brought it down to lambda, which was lambda 0 by B. Is that okay? You remember this one? So, this was lambda 0 and this is lambda, and lambda 0 by lambda is B. Okay. So, we make another change of variable. Now, I am not going to do the algebra. Then the equations appear like that. Okay. This is my RG equation. These are called renomination group equations. So, how RL bar is changing under RG operation, which was combination of coarse graining and rescaling. Okay. So, what is the correction under this operation? If I was not doing well, basically these are the important contributions, these are the corrections. Okay. So, this is the differential equation. Now, I would like to study the properties of the differential equation, and those properties will tell us about the properties of phase transition. Okay. Now, that is a crucial part, that is why for which Wilson got the Nobel Prize. So, from this we can say something about the phase transition, in fact very interesting aspects of the about the phase transition. Okay. So, first thing is, so if you have studied dynamical systems, we look for the fixed point of this equation. What is the fixed point? Fixed point is when fixed points are points where if you are sitting at those points, you will be remain there forever. Okay. That is a fixed point, no, my definition. So, if I am staying at that point, I will remain there forever. So, what is the condition I should impose on this equation to obtain the fixed points? I should set the derivatives to be 0, right. So, if I set dRL bar to 0, then RL is not changing. So, you set both these equal to 0 and that will give you the fixed point solution. So, look for RL bar and UL bar for which these two equations are 0. Okay. It turns out there are two fixed points, okay, and that is what we will study. In fact, one fixed point you can easily guess. What is one fixed point? 0 0 is a fixed point, no. If RL is 0 and UL is 0, then it will remain there forever. Okay. So, that is a fixed point, and please remember one more point. Okay. Now, since we are doing a lot of complicated stuff, R0 was T minus T, small t, which is T minus Tc. What is T minus, what T is temperature and Tc is the critical temperature. Okay. There is a proportionality constant, you may put some constant here alpha, but is proportional to T minus Tc. So, T is the temperature. So, what do I do when I go from paramagnet to ferromagnet? I decrease the temperature slowly, I reach the critical temperature, that is a fixed, that is a transition point, and I decrease it even further, then I reach ferromagnet. So, T equal to 0 or R equal to 0 means I am at the fixed point, I am at the transition point. Okay. You have to just follow the thread somewhat. So, this is one fixed point, and u being 0 is the nonlinear term is basically not, well, I am sitting at a point where nonlinear term is not playing much role. If I look at, by the way, this is a, well, we are going to go around the fixed point, okay, and we will study the properties. So, there is one fixed point and the other fixed point is slightly non trivial. Okay. So, let us study those two fixed points. One is called Gaussian fixed point, which is what I said 0 0. Okay. And as I said, this is, in fact, you can just have a look and you find that 0 0 is the solution. Okay. This is two solutions, and we choose a parameter called epsilon, which is defined as 4 minus d. Okay. So, I am going to work with d greater than 4. D is a dimension. Okay. So, in the integral you have k to the power d. So, d is a dimension of space. So, we live in 3 dimensional space, or if you are working with 2D spins and it is 2D space d equal to 2, or it could be 4 dimensional space. In field theory you are allowed to go to any dimensions. Okay. And 4 dimension has very interesting properties as you see right now. So, epsilon is 4 minus d. If d is greater than 4, then we get epsilon is negative. Okay. So, now here I will linearize around fixed point. So, this is standard thing in nonlinear dynamics. Okay. Linearize means I make a perturbation of UL. So, I make this thing UL minus UL bar star. Okay. So, this is a fixed point UL star and this is my small parameter. So, I call it delta UL, but right now UL star is 0. So, my delta UL is same as UL. Okay, is that clear? So, this is what we do. So, here, so if I do this, so look at the first equation. So, first equation dl RL bar, this is the perturbation around the fixed point. By the way, my fixed point is here 0 0. I make this as x axis R bar, y axis is U bar. Okay. Now, I am here, I go slightly beyond the fixed point. Okay. Now, I do linear perturbation. So, I am going to drop the nonlinear terms. So, here is going to be 2 RL bar half UL bar and 1 divided by the way, this is a nonlinear term, no? Nonlinear, correct? I mean this. So, how do I linearize? I take this to 1 plus RL to the power minus 1 and I do Taylor expansion. If I do Taylor expansion, what will this becomes? This term is 1 minus RL bar. So, UL RL bar is nonlinear, right? A product is nonlinear. So, this approximately 2 RL bar plus half UL bar. Okay. So, this is what I keep. This is valid if you are close to the fixed point. Okay. What about the second equation? DL bar UL bar. So, first term is epsilon, 4 minus d is epsilon, epsilon UL bar. Second term, what happens to second term? Is quadratic, and below if I do Taylor expansion I am going to get, I cannot get something below quadratic, correct. So, the second term is nonlinear already, it cannot become linear, there is no linear contribution. So, this is 0. Okay. So, this is my linearized equation. So, we can write down the linearized equation in a matrix form, that is my next object, right. How do I write this in the matrix form? So, I write d dl RL bar UL bar equal to RL bar UL bar. Now, what are the matrix coefficients? So, first will be 2, right, 2 RL bar and half, below 1 0 and epsilon. So, this is my matrix. Now, what is next? So, given a matrix you find the eigenvalues. Okay, this is very standard operation, linear algebra, eigenvalues and eigenvectors. Okay. Now, some simple properties which I will just state it right now, but then we will I will not compute the eigenvalues by hand, but I will just tell you the result. So, this is my fixed point. Now, this 2 by 2 matrix in general it will have 2 eigenvalues and 2 eigenvectors. Sometimes eigenvectors become 1, okay, not 2, but always it has 2 eigenvalues. It could be degenerate or non degenerate. In fact, you can guess the eigenvalues here. What is the eigenvalue for this case? Some quick witted mathematicians. So, the trace is 2 plus epsilon and determinant is 2 epsilon. So, the eigenvalues are 2 and epsilon is in fact very straightforward. So, eigenvalues are 2 and epsilon, and the eigenvectors we need to check, we need to compute. Now, the simple properties, if the eigenvalues right now epsilon is negative, right, this epsilon is negative, and so one eigenvalue is greater than 0 and one eigenvalue is less than 0. Okay. So, let us say, so it turns out if it is positive, then what is the solution? For the positive eigenvalues, in fact, this is what we were discussing some time back in the lab. So, x dot is alpha x, x prime along the eigen direction, alpha is the eigenvalue lambda, let us put lambda eigenvalue. So, here if lambda is positive, then it will grow, right, x will grow. In fact, x will go as e to the power lambda t x 0. If lambda is negative, then x will shrink. So, here this I start from somewhere, it will go towards the fixed point. If lambda is positive, then it will go away from the fixed point. So, one is unstable direction, if lambda positive, then it is unstable direction for the eigenvector, and if lambda is negative, then it is a stable direction. Okay. So, this is a standard nonlinear dynamics language. You might have done this in your classical physics, I believe, I do not know. So, this is how we will do it for this, exactly same language. So, I am just going to tell you the result. Okay. So, the two eigenvalues 2 and epsilon. For 2, the eigenvector is 1 comma 0. So, this is my RL direction and this is my UL direction. 1 0 will be horizontal, no, x component is 1 and y component is 0. So, this is the one eigenvector, this one corresponding to 1 0, this is the eigenvector in both the direction. I mean 1 0 is one of the vectors. You can put, instead of 1, you can put alpha can be any number that will satisfy the that will basically satisfy the equation, the eigenvalue equation, okay, eigenvector. So, this eigenvector, and what is the, is it stable direction or unstable direction? Eigenvalue is 2. So, it is an unstable direction, it is going to flow outward. So, if I start from here, it will grow. So, here UL is 0, by the way, right, UL is 0. So, any RL I start with, RL will keep growing. Okay. So, that means if RL is positive, that means temperature is greater than Tc and the temperature will keep growing. So, it becomes more and more paramagnet, okay, I mean more and more disordered type. Okay. If RL is negative, then it will become more and more negative, that means it will become more and more ordered, because this is what you can interpret. So, this is that direction. Other direction is epsilon, which is negative. So, this is a stable direction, this is eigenvector is this. Okay. So, I did it by kind of visualization, and the eigen directions is here. In fact, it is correct, epsilon is negative. So, y is positive, but x is negative. Okay. Here, so if I start from somewhere here, it is going to go towards 0. So, what does it tell you? That UL, whatever I start with, it is going to go to 0. That means, the nonlinear term is getting more and more unimportant. UL, remember, was the nonlinear coefficient of the nonlinear term, right, UL phi 4. So, nonlinear term you can ignore if you are near this fixed point. Okay. So, what does it tell us? That for d greater than 0, if my dimension is 4 greater than 4, then I can work with a linear problem. Okay. and I can get the property from the linear well, you need some nonlinearity to begin with, otherwise you can't get a phase transition. Okay, phase transition requires nonlinear, but it becomes less and less important. Okay, so that is what it tells you. And it turns out that this is a Landau theory. Landau basically what does this idea tell us, that nonlinearity, using nonlinearity you can get the magnetization, mean field theory. Okay, you might have done mean field theory in StatMech. The value of the mean field theory will remain the same, will remain the value for the magnetization. There will not be any fluctuation. Fluctuations will become unimportant, they will become very small in d greater than 4. Okay. So, we use a nonlinearity to get basically the magnetization mean value, and we did that mean field theory much before. Okay. And you can just look at standard Landau theory for for magnetization, that is what we solve. Okay. In fact, it is just phi minus phi cube, right, phi. So, this was we set it to 0, and that is our that is solution phi bar equal to 0 and phi bar equal to plus minus 1. So, it comes from Landau theory, and that will be the correct theory, and it has certain properties. Okay. I will tell you some properties bit later. Okay. So, this is a trivial fixed point, is called Gaussian fixed point. Here the fluctuations are Gaussian, like in thermodynamics you say no, the fluctuations are Gaussian. So, basically we get temperature as the mean temperature, and the fluctuation around the mean temperature is negligible. Well, it is Gaussian, so it decays very quickly. Okay. So, this is Gaussian approximation. Now, let us go to non-Gaussian fixed point. Okay. So, this is the non-trivial one for which Wilson got the Nobel Prize. Okay. So, this is, and this is approximate solution. Okay. This is not exact solution, but I think that is what they did in their work, and they got the. So, I will tell you how to get this. So, we again get the fixed point. So, this is non-Gaussian fixed point, but we will assume d less than 4, but I am going to again use the same variable d, epsilon is 4 minus d, but now since d is less than 4, epsilon is positive. Okay. So, as a result, what happens to the fixed point which is at the origin? So, the linear equation around origin will give you the exactly same fixed point 0 0, the 0 is the fixed point, and what are the eigenvalues? The solution remains the same 2n epsilon, but epsilon has become positive. So, the two eigenvalues both are positive 2n epsilon. So, this fixed point becomes unstable. That means, wherever I start around the origin, I am just going to be pushed away. So, I am not going to go towards this fixed point, basically I just go away. So, that is where this fixed point is uninteresting, actually unimportant for d less than 4. For d dimension 3 dimension, you cannot use that fixed point property. So, the new property, new fixed point is important, and the new fixed point I had to just again obtain by setting this to 0. Now, this equation looks pretty complicated if I want to do analytically. Of course, in a computer you can do it easily in Mathematica or numerical Python. So, one idea you can look at the first equation. Okay. So, I need to solve it the first equation. So, I need to drop the nonlinear term. Okay. So, here start with second equation, second equation is better. Okay. So, UL is not 0, UL bar, UL star actually, the fixed point is need not be 0, I am going away from the fixed point. So, second equation I see 4 minus epsilon UL bar equal to 3 by 2 UL bar squared 1 plus RL bar squared. Okay. UL is not 0, so that goes away. So, that gives us UL bar is 2 by 3 epsilon multiplied by 1 plus RL bar squared. Okay. So, I just did it from here. So, now I am going to say, well, basically RL bar is not too large, okay, not close to 1. So, I will basically drop this term. So, UL bar is roughly 2/3 epsilon. So, RL bar is much less than 1, that is the assumption we make to solve it. That is what Wilson did, I am not doing it. I recommend that you can do it more carefully and numerically. Okay. So, this is this one solution. It has become non-zero now, right, but I should put a star here. No? So, these are fixed points. So, you should put stars, okay, 2/3 epsilon. Now, you can plug that in the first equation. The first equation gives us what? 4 RL bar, well I am just putting 4 here, equal to minus UL bar divided by 1 plus RL bar star, okay, so star. Okay. So, again RL bar is much less than 1, so I can drop this. So, RL bar is minus UL bar star by 4. So, put this 1/4 into 2/3 epsilon is minus 1/3 epsilon. Okay. So, this is you do it analytically, of course, this has done in this paper I think appeared sometime in 1970s, okay, late 70s, 75 or something. Okay. So, that is what they did. Now, I need to study the properties of the eigenvalues and eigenvector near this fixed point. So, these are fixed point, is one point in the phase space. My phase space is 2 dimensional RL bar and UL bar. Okay. So, okay, so basically it turns out the nonlinear term becomes important for this problem, because UL bar is not 0 anymore, and it is important. And I think we argued it before, the fluctuations are important for d less than 3, d less than 4. So, since fluctuations are important and nonlinear term is significant, what do you do for perturbation theory? So, perturbation theory says that nonlinear, the perturbation parameter must be small. Okay. So, that is another argument which is made by them, is that I am expanding near d equal to 4. Okay. So, so this is called dimensional expansion. Okay. So, basically I am varying dimensions, but I am close to d equal to 4. Okay. And you will see what the tricks, how it is used in couple of slides later. Okay. So, the eigenvectors for the two well, this is a fixed point, I can linearize it, is bit of work, but you can do it. So, this is my vector, this is matrix, sorry, this matrix. It has two eigenvalues, 2 minus epsilon by 3 and minus epsilon. So, epsilon is positive. So, what happens to minus epsilon? Negative. So, one eigenvalue is negative, and what about this? Epsilon is 4 minus d and d is near 4. So, epsilon is small, okay, it is like standard epsilon being small. So, my epsilon is small. So, my eigenvalue is close to 2. Okay. So, and my eigenvectors are these. Okay. So, I made a sketch only, I did not do it, but I would recommend that some of you can do this in Python or Mathematica. Okay. One, this picture I want to, I already told you about, the 0 point has become unstable. Okay. So, it is going to go to the new fixed point, the flow will go to the new fixed point, and the new fixed point is here, new fixed point. Okay. It turns out that UL bar is positive and RL bar is negative. Okay. 2 minus epsilon by 3. So, okay. So, sorry, so that is that stuff. So, epsilon by 6, what was it? Epsilon by 6, and one of them was epsilon 2 epsilon by 3. So, this 2 epsilon by 3 y direction, and this minus epsilon by 6. Okay. It turns out, so the eigenvectors are this line 1 0, in fact, it is similar to what we had before, and the other eigenvector is along that direction, this one. Okay. Now, it turns out 2 minus epsilon by 3 is greater than 1, right, greater than 0. So, this is unstable direction, and this is stable direction. Okay. So, what happens to UL bar? This guy is again going to go towards this thing, but UL bar is finite. UL bar is not 0, is finite. So, I basically come to finite UL bar for the new fixed point, and this fixed point will determine the property of phase transition. Okay, I am going to show you in a while.